I mentioned, Peter, one of the sessions that I was doing at the Mobile World Congress in Barcelona, there was titled "Everyone Can Be a Quantum Developer." And then he asked me politely, can you do that in 2 days' time? Yeah, why not? I still have everything prepared. So this session, it's a session that I gave to some 400 people, uh, where there were 398 of those did have absolutely no idea about quantum. But the goal of the session was demystify a little bit how difficult it is to get your hands on. Basically, do a hands-on session, show you actual code. So there's no PowerPoint or anything. It's just a Jupyter notebook where I'm going to show you some of the magic that quantum brings. And I'm going to be using Qiskit, but there are other frameworks out there. And please ask any questions or throw any ideas or comments, and we'll go as far as we can get in this session. So let me start with if I manage to share my screen. Here we go. Just give me a sec. All right. Can you see my screen? Oops. All right. Terrific.
Yes.
Thank you. So what you're seeing here is probably most of you are familiar with Jupyter Notebook, whether you use them on a daily basis or not. It should be relatively familiar for those in any kind of data engineering or data science roles and whatnot. And it is not surprising that quantum computing has used and leveraged a lot of the tools and libraries and frameworks and programming languages that we've had historically in the data world. At the end of the day, machine learning is algebra and quantum computing is nothing but glorified algebra to some extent. You may remember from the few sessions before that we did on quantum computing that, yes, this is one of the different shapes and formats that a quantum computer has. This is specifically a superconducting device. But what you see here, this golden chandelier, as we like to call it, is nothing but a very expensive freezer. And the chip itself goes right underneath at the bottom of that chandelier. And that's where the qubits are hosted in something that actually resembles a little bit a normal chip that you would see anywhere else. In fact, if I show you a quantum chip and put it in front of you together with some other types of chips or FPGAs, if you don't know exactly what you're talking about, then you would think it's a perfectly normal classical device. Now, the question is, how do you program a quantum computer? So you may see all those blue cables and things hanging from there that it looks like a really bad network engineer went to the data center and left everything hanging. The way these devices, this is a very general way, in superconducting qubits at least, is some control mechanisms that effectively throw electromagnetic pulses to the chip so that the quantum state of that qubit, set of qubits, if they are entangled, change. So imagine you send a sine wave, like a pi halves or a 2 pi wave bound frequency with a very specific tune-in. You hit the qubit with that specific wave, and that sends the qubit to the state 1 or to the state 0 or anything like that. That's all we do. Of course, with a lot of control and optimization, but effectively that is all we do, sending EM waves, other type of waves if we use photons and so on, but any type of waves prepared and calibrated in a very specific way to the qubit. The way we create those waves is through control mechanisms on specific devices that are connected to the qubits. And in fact, one of the limitations or one of the challenges that we have today in quantum computing is the scalability of the control mechanism, because a lot of those coaxial cables are the little things that carry that signal over to the qubit. If you want to make a 1 million qubit device, imagine 1 million coaxial cables running into the qubit. So that is one of the engineering, but not physics, not physics problems, engineering problems on miniaturization and so on that the industry has today. How do you create those pulses? a series of languages and low-level languages such as quantum assembler. If you are as in a similar age as me, you may have used some low-level programming languages in the past. And obviously, we used assembler back in the day to program our PICs and so on, and our EEPROM chips. So we have something similar, a quantum assembler that speaks with the control devices to create those waves. We don't think in terms of I need a pi halves wave with this type of frequency, with this type of oscillation. We just think in terms of this kind of quantum assembler. And because assembler or quantum assembler is not super user friendly to create advanced software, then we have different frameworks that transpile it back. And the weapon of choice for the vast majority of cases out there is Python. And then in Python, there's quite a few frameworks available to get started in quantum computing. The one that I'm going to show you today is Qiskit. I personally say Qiskit. Is a framework created by IBM and arguably the most extended in the world. IBM has been able to create a massive community. They've done a really good job at creating both local and global communities and doing summer camps and all that. Creating a big textbook that used to be the main textbook for everyone for a long time. Now they passed the earlier in the year the version 1, so it's now the stable version, and that they have functions and a lot of other stuff. But Qiskit is probably one of the best sources to start your way into quantum, and because it's pretty standard Python, anybody who's used the data industry will be able to jump into it easily. But before we get into the code, I want to play a game, and I think it's going to be fun because there's not that many of us. So I want to play a card game, and I'm going to explain to you how it works. This card game has 2 players. We're going to call them Alice and Bob, because that's how everyone is called in the quantum world, right? And the game is really easy. Player 1, Alice, has 1 movement, which is either flip the card or leave it in the way it is. The card starts looking up, and Alice can decide to flip it or not flip it. Then Bob goes in. Bob can decide to flip the card or not. And Alice comes last. Alice has 2 movements. Alice can decide to flip the card or not as her 3rd movement. All right. The winner of the game is if the card ends up looking up, Alice wins the game. If the card is looking down, Bob wins the game. Easy peasy, right? It shouldn't be too difficult. Now, you may think that game is ridiculous because obviously Alice has the final word. Yes, except the movements have to be predefined and without any of the other players knowing, right? So you have to write down your movement first. Alice writes down her first 2 movements and Bob his own movement. And then we figure out who wins, all right? So I need 2 volunteers. I think I'm going to use Peter. You good with that?
Yeah.
And maybe Diego, just for using another English person. All right, so Peter, you're going to be Alice today.
Okay.
And Diego, you're going to be Bob for the rest of the day. So I'm going to keep calling you Bob today. Maybe
I'm
for
not
the
trying
rest
to
of the
switch.
week.
Based on my previous experience, I'm not trying to switch on my camera. Sorry.
That's all right. So just a very quick example on how this, right? Example 1, the card starts up. Alice decides to flip the card, goes down. Bob decides to flip it, goes up. Alice decides to leave it as is. The card stays up, so Alice wins. Easy. Another example. Alice decides to leave the card, stays up. Bob flips it, goes down. Alice decides to leave it, stays down. So Bob wins in this case. Right? Are we good?
Yep.
All right. I'm not sure how am I going to do this so that you don't know the other player movements. I'm going to have to trust you guys, okay? Just think your movements first. All right. So what you see here is I'm importing some Python libraries. That's fine. And I have created a pretty normal and straightforward Python code to simulate this game. Right? I have some functions that decide based on a variable what's the movement from each player. I have this method that decides who wins based on what is the state of the card at the end. So if the card is ab, which I represent as 0, or the card is 1, represented as 1, so Alice wins if it's a 0. And then I build the quantum circuit. This is obviously the key that is a bit more tricky, that builds this game classically. By this, a quantum computer can actually implement any logical gate that we normally do with our transistors in classical computers. So I am implementing this classical game on a quantum device. In this case, is in my laptop where I am simulating 2 qubits. All right? So I'm creating a quantum register, which represents the card, and I create a quantum circuit, and I'm creating a few quantum gates here, and all the if-else's that this movement does. I will be able to share these notebooks afterwards if anyone is interested. All right, so I have here a little widgets on Jupyter to get the movement. So please, Alice and Bob, think you've moved your movements. And then on the count of 3, I will ask you to shout at me back your movements. 1, 2, 3.
Flip.
Flip.
So Bob is flipping, was it right?
Yeah.
And Alice, you had 2 movements, flip and?
No, I said flip.
But you have 2 movements. The
Oh,
first one
2
and the third one.
movements.
Yeah.
Flip. No, flip.
So 2 flips, right?
Yes.
All right. Because Alice goes first, then Bob, and then
Yeah.
Alice.
Yeah.
I know it's quantum computing, but this is an easy game. All right. So I build a circuit here with this little thing here, is the same method that I showed you before. And this is the logical gate, or quantum gate in this case, that makes this decision. Flip. So all of you decide to flip the card all the time. I don't know why it appears twice, but bear with me. I run it, and as you would expect, the card stays up, Alice flips, then Bob flips, then Alice flips, the card ends down, so Bob wins. Congratulations, Bob. You've done a great job. So I'm going to stay with Bob for a second. Thank you very much, Alice, for your
Sure.
help, even without a camera. So now, instead of Alice, Bob, you're going to fight against a quantum computer. Are you ready?
Yes.
All right. Only one movement. You can choose flip or not flip. Not flip. Right? You're not flipping the card. And the quantum computer is, of course, it has some magical powers. Right, that classical devices don't have. You all have heard about quantum devices being able to use the multiverses and teleporting and stuff like that. So it has magic. So instead of flipping or not flipping, the quantum computer applies magic, right? And it applies magic, then you have decided to flip, and the quantum computer applies magic again. And then if we simulate the circuit, exactly the same as before. In this case, I'm using something called the AIR simulator that effectively is simulating the quantum system for me. Second, something is not. What's going on?
I beat the magic computer.
Yeah,
You just beat the.
And there
You beat
go.
quantum.
You just beat the computer.
Quantum supremacy is here.
Something is happening. Hold on. There we go. This is the reason I don't like Jupyter notebooks. So now I run the circuit properly, and the card is up. So Alice won. Sorry, Bob, you lost this time. In fact, we could play this game as many times as we wanted. And as a matter of fact, we played 1,024 times. But I didn't want to keep you guys bothered with hitting the button so many times. And you lost every single time. Now, it doesn't matter whether you flip or not the card. Something weird is happening here. Right? You see all this 1,024 all the times, and the output was a 0. I'm going to just go out on a limb, because most of you have heard that quantum devices are not perfect, right? They're noisy. They bring in errors. So if I execute this using the normal profile of a normal device, this is the simplest quantum computer, quantum circuit that you can get. In fact, Mr. Bob, Diego, you would have won twice out of 1,024 trials. That is because our quantum computer got some errors, maybe because of some radio signal coming into the quantum computer, maybe a gravitational wave, maybe a neutrino coming by, any reason that the bit flipped and that introduced an error in the system. So what we have done here is applying a quantum gate instead of a classical gate. This game effectively used a NOT gate, right? The typical NOT negation that flips from a 0 to a 1 or a 1 to a 0 when you flip the card. But the quantum computer has something called superposition. And that was this magical power of a pure quantum gate that applies the system and puts it in a different kind of position. Hopefully you guys are now saying, what the hell is going on? I don't understand anything. I'm going to try to move over to another notebook and try to give you a little bit of light on what has happened here. So again, I'm importing a few libraries, Qiskit as the library that I mentioned before, but then NumPy and some others that are maybe Matplotlib and Plotly and so on, libraries that probably are well known for the usual suspect in data science. And one way of thinking about a qubit, and mind that this is not an accurate representation, but one way of thinking about this is a spinning coin. If I put a coin spinning like this, and I ask you, is this heads or tails? You probably would say something like, well, neither, but at some point it will be one of those, right? You're not saying, when the coin is spinning, you're not saying it is heads and tails at the same time, as we typically say with qubits, which is a very inaccurate depiction of that. It's neither of them, it's both of them, but it's in an indeterminate, in an uncertain state until the coin collapses on the table, or until we make it collapse and look into the coin and we say, hey, it's actually heads, it's tails, all right? So you can think of a qubit in a similar way to this coin. It's not a 0 or a 1, but it's something in between. Now, in the moment that we look at the qubit, that we measure it, you can think of it as the famous Schrödinger cat. In the moment you look into that is when you have the 0 or the 1 available for you. But when the coin is spinning, during this period of time is when we can implement, when we can apply quantum gates into our qubit. For example, the magical one that we had before. Once the coin is on the table, heads or tails, that's it. All the quantum magic is gone. And that is why one term that maybe you have heard in quantum, the coherence times of a given quantum device is so important, because that tells us for how long we can keep the qubit spinning, applying this magic into the qubit, or our circuit that represents the mathematical problem that we are solving, before we measure. And when we go and measure, when we look at all the coins, is when we see what is the output, what is the solution for our problem. But let me try to make it a little bit more clear for you. So I'm building a quantum circuit here, right? Same instruction, quantum circuit. This one, say, means it's one qubit. And the way we represent qubits normally is with a sphere. We call this sphere the Bloch sphere, B-L-O-C-H sphere. So I haven't done anything. I just created the qubit, put it on the circuit, put it in the simulator, and say, can you represent this sphere for me? And effectively, it's a 0, and the 0 we represent it as being up there in the North Pole of the sphere. It does have this little symbol in there. We call it a bracket because, quantum mechanics, but bear with me. Just imagine that's a 0. Likewise, I could take the same circuit and apply an X gate, or in classical computing, we would say a NOT gate. And that means that I do a bit flip. So I move the 0 to a 1, and then I get a fantastic 0. Easy peasy. right? But what if I was able to do some magic into this qubit as long as it's spinning, and I apply a gate that is represented by an H in Qiskit, it comes from Hadamard. And the Hadamard gate, what it creates is the famous state of superposition. So this thing that you guys see here is, oh, it's 0 and it's 1. So what on earth is going on? This is effectively a qubit in a superposition state. Or imagine a coin spinning like that. If there is any physicist in the room, mind that the coin is not an accurate depiction because qubits have phase. And coins are classical systems without phase. That's why in this library we have phase here. And the state 1 is in that opposite phase on the system. But this circuit now is in that superposition state until I measure it, because I am simulating it. I can present it like this. In the moment I measure effectively in my quantum computer, it will be either 0 or 1 with a 50% possibilities. I measure 100 times, 50 times will be 0, 50 times will be 1. Let me move forward a little bit. I'm going to use 3 qubits, and I'm going to apply, 2 qubits. Okay, I'm going to apply the Hadamard gate to the 2 qubits, to both of them. And then I create the same sphere. Now, because I have 2 qubits, I suddenly can put the 2 qubits or the 2 coins in superposition of all the different options that I have: 0, 0, 0, 1, 1, 0, and 1, 1. So far, this is behaving almost like a classical device, except now I can encode information everywhere in the sphere. With bits, that's it. You get 1 bit and you're able to encode 2 possible bits of information. Either something is 0 or something is 1. But in the moment you have your qubit spinning, you can put information in almost an infinite amount of possibilities here, and you can put all that together. So if I go to 3 qubits, I can create a quantum circuit with 3 qubits. I can apply Hadamard gates to the 3 of them, and I can do something funny. I can start getting all those qubits together by using specific types of gates that's almost like hand holding them. And I'm using this gate here called CZ, controlled set, between qubit 0 and qubit 1. And what's happening here is that 3 qubits, we have 8 possibilities, right? 2 cube, 2 times 2. So you have all the possibilities, 0, 0, 0, 0, 0, 1, and so on. But those qubits with where the last 2 numbers are the same get entangled. And that is why they are somehow related now by these chains of phase. This is what this gate has done. If these qubits are the same, please change the phase of those 2 possible states. We still have 3 qubits. And in fact, I can draw the circuit. And the way we draw quantum circuits is by having 1 line per qubit. And then we apply the gates as if it was in a temporal way. So we first applied the Hadamard gates, the magic gates, we called them before. And then this controlled set gate that is represented by these 2 little dots in here. And everything this is doing is marking, and mark my words, it's marking these 2 states out of 3 qubits so that we can do stuff with them later. Let me quickly show you something. There is this tool here that I love to use it when I show how this works. So this is the same block sphere that you saw on the circuit before. And here is how we represent it for those mathematicians. Here is the Euler formula on representing any point on the sphere, right? You can use your complex number formulation with E, and then you can move your quantum state or your point in the surface of the sphere anywhere you want, and that represents the qubit state. So this means that if I start my qubit at 0, that's how qubits are normally started, I can apply a gate X, boom, and it goes to 1. I can apply the Hadamard gate, and it goes right to the equator, to the state plus that we call, it could be plus or minus. So if now I give an X, it will move the phase of the qubit, but I can apply any arbitrary gate. In fact, I can move any angle I want. I can start putting things like S gates, Z gates, H, T gates that change the phase, and so on. So all these gates are things that I can program. I can code them with Python and move the qubit anywhere I want. Now, you may have realized that now that the qubit is here somewhere around, I don't know, Gothenburg, maybe, the probability of getting a 0 when I measure is much, much higher. Something like, what, 90%-ish? The more I get close to the 1, it's almost like if I am adding a bias to my coin, so that 90 times out of 100, I always get heads. Likewise, if I move my qubit here with quantum gates, adding any gates into my circuit, I am changing the probability of getting a 1 or a 0 when I measure. And this is all mathematically defined with this representation of the quantum states, the quantum state. This is the last part of the presentation where I show you something with that mathematical shape. But let me try to get into a bit more detail on superposition. So I'm building a quantum circuit with 5 qubits, getting bigger and bigger now. I am adding Hadamard gates to the whole collection, but I'm also adding a NOT gate and an H gate. So this is the representation. Now things get a little bit more complicated, but still is following the same path. You get these magic gates that put everything in superposition. In this specific case, I initialize it 1 right here on the qubit 4. I want it to be a 1 before applying the Hadamard gate. And then I am marking one specific qubit. What this gate does here is this a multiple control NOT is that in the cases where all of these states are 1, this part here, the qubit 4, will flip. It's almost like a NAND gate, if you recall, but I can add as many controls as I want. So when there is a 1, 1, 1, 1 here, it would flip whatever comes in this direction. Now, here's the mind-blowing element. Is it always a 1 in here? Well, no, because we have a superposition state. So we are playing with all those possibilities at the same time. And we can represent that with the sphere like this. Now the sphere is pretty skewed towards a very specific part of the sphere. And what I have done is that the state 1, 1, 1, 1, 1, 0 has been marked to do something with it afterwards. I could change that any way I want. So I can say, no, I am interested in marking this specific state only. Oh, hold on. Here we go. I want this specific state. All right, that's fine. And I'm going to need when I represent this on the sphere, now this is different, right? So this comes from the definition of the problem that I want to create. And if I go and measure, I can see that it doesn't make an impact, right? I have almost a uniform possibility of getting any of the states out there. So why are we doing all this? This is at the end of the day, like spinning the coin and doing that 1,000 times and seeing all the different possibilities. This is not helpful yet to do absolutely anything. So let me show one more level how this works. we have seen how the X gates work and how we can initialize, say, for example, a qubit with a circuit with 3 qubits where there is only one state. In this case, it's 3 qubits that start with 0. I did not put any superposition. I just added the identity gate, which does nothing. It just moves everything. I could just not do anything. 3 qubits, they start at 0. So if I look at the block sphere, it does absolutely nothing, right? There is no superposition. Of course, as now, I could add all the superposition and some NOT gates, and then I get all this. That's by adding the magic. So if I go and measure and plot the histogram, by having superposition, I can get all the possible, all the potential 8 states with almost equal outputs. Now, if instead of doing that, I remove the Hadamard gates, now the only possibility is 1, 1, 1, because I didn't put any superposition at all. So let me get into a bit of a more complicated situation here that will help you understand how do we use these properties to design a quantum circuit. Now, you may have seen when you throw a couple of stones into a lake and the stones create some waves, right? And those waves in some points, they build on each other. And in some other points, they cancel each other. One wave is having its peak, the other one is having its valley, so they cancel each other. It's almost the same principle that our noise canceling headphones utilize. They hear what is outside and they try to create a sound wave that is as similar as possible, but opposite, so it cancels the noise outside. That is the same principle that we try to apply with quantum computer. We think what is the mathematical structure of a given problem, and then we try to use interference to, once we have, let me get back to my superposition state. Once we have all these many possibilities, we ask ourselves, how can we eliminate all the possibilities that are not the answer to my problem? So I'm going to try to show you this in the best way possible. And what I'm going to show you is something that we call a Grover's algorithm by Lev Grover, which is one of the most important algorithms that we use in quantum computing. And it's an algorithm that can be used to search with a quadratic speedup on an unstructured database, for example. So what has happened here is that I am creating an oracle. An oracle is a little device that knows how to represent the rules of a given mathematical problem. So let's say I'm looking for the solution of a Sudoku. The Sudoku can be an NP-hard problem because it grows with size. It's really easy to check whether the solution is correct or not. But the bigger the Sudoku is, the more difficult it is to find a solution. If I give you the 10 by 10 Sudoku that you find on the newspaper, it will take you a minute or 2 or 5 minutes to solve it. The computer can solve it in half a second or less than that, but it's really easy. If I give you a 40 by 40 Sudoku, that's slightly more complicated, and you would need quite a lot of compute to solve that. But if I give you the solution, you will be able to see whether it's correct or not because you know the rules. You cannot have the same number twice in a row. You cannot have the same number twice in column. You cannot have the same number twice inside the box. You know those rules. So what we are applying here in the oracle are those specific rules. Let's talk in terms of something that we are all familiar with. Let's say we have a portfolio optimization problem, and we have some very specific rules to follow in terms of constraints of the portfolio, the Sharpe ratio that we are willing to accommodate, the correlations between the assets in the portfolio. You know the rules of that game, and that's what you typically implement your classical optimizers, whether you use Cplex or PyPortfolio or any of the other tools. But of course, the more assets you have in your portfolio, the more combinations, and the more the problem grows in an exponential manner, right? So what if we could embed those rules into this type of oracle in the mathematical way? So I have created this. I know those rules, and for simplicity, I know that the solutions are 101 and 110 in my super mini Sudoku solver. And I'm applying this circuit. I'm not going to get into the details on how the algorithm works because it would take me a 5-hour session. But if anyone's interested, happy to get into that. And I'm going to go slowly into it. So we first create the circuit in superposition, 3 qubits. We add our Hadamard gates. So now we have all the possibilities. As we were seeing before, all the options can happen with equal probability. Now we want to apply the rules of our game, which we do with this kind of oracle here. And now what we do, if I show you this, these states are marked. Now the rules of the mathematical problem have marked those qubits, but this still does absolutely nothing. If I measure this now, even if those states are in red, you will still have the same amount of probabilities to get the right answers together with the wrong answers. What I'm doing is apply this diffuser part of the algorithm, this part here, which comes from this specific method. And what this thing is doing is reducing the probabilities of the wrong answers and increasing the probabilities of the right answers on the algorithm. Again, if anyone's interested in knowing how specifically that happens, I'm happy to have a more dedicated session. But this is a little bit similar to what I was showing you before, right? It's identifying those marked elements and doing something really smart with these waves that we send, almost like the noise canceling, so that when I go and measure them, now, as you can see, I can only measure those 2 states that I was looking for. And if you see, those little dots are now much bigger. The dots in this library, the size of the dot represents the probability. So before we had equal probability for all of them. Now, when we measure, we will only have those states. Before that, we would have had to poll classically the whole system. It's almost like, imagine I give you the yellow pages and I tell you, can you give me the phone number for Peter's restaurant? And then you would go, you would look alphabetically, and you will get the number. Easy peasy. But what if I tell you, hey, I have this phone number, and you tell me who owns it? Because the yellow pages are not indexed for that purpose, at least in the old days when we had this book, you would have to go through the whole book. And on average, if you did this quite a few times, you would have to go through half of the book on average to find the solution for that problem. What we're doing with this is encoding that problem into the circuit, and then you would do that in the square root of that. And in fact, if I go and measure it and I simulate it, I am transpiling it first into quantum assembler. I am running it on a simulator, of course, and I'm getting the counts of the simulation, which is roughly 1,000 shots. And indeed, with equal probability, I get the 2 answers of the problem that I was looking for. I'm going to end with just one note, because obviously this is a really simple problem and it's a little bit difficult to understand the implication. But let's say I want to decrypt RSA. Now, in order to decrypt RSA cryptography, I need to solve a very specific mathematical problem. I think we talked about this in a previous Zenith session. I need to solve the mathematical challenge of finding the prime factors of the number that was used to create that specific asymmetric key. That is a very difficult problem to solve for a classical computer, but happens to be a relatively easy problem to solve for a quantum computer. So what you see here is the circuit that I built to the circuit that I built to crack the internet. And what you see here is obviously a much more difficult circuit that is also made only to find the prime factors of the number 15. And obviously we all know that is 5 times 3, but it's the same circuit that would grow and scale to find a number 4,000 long once we can put as many lines here as qubits needed, which is about 1,000,000 qubits. So what this is doing is first building a circuit that that finds the modulus 15 for the number. Then it creates something that we call the quantum Fourier transform, which does what, if there's any telecommunication engineer in the room or data, you may remember your old days on the Fourier transform. It's basically trying to find the periodicity of a given for a given signal. So that's how we calculate the modulus. And we create the circuit. We apply superposition. So that's exactly the same as we did before, all these Hadamard's here. And then we are applying this little in each of the qubits, and then finally this quantum Fourier transform. This is called Peter-Shor algorithm, and it's obviously the algorithm that generated all the fuss about breaking the internet. So what you see here is no more, no less than the Python code required to break the internet. At least if we only had 15, two digits RSA certificates. I'm just going to finish with one little note here, because a lot of you have heard about quantum machine learning. Quantum machine learning is a little bit more complicated, but also possible. So let me show you something very quickly. I'm getting the MNIST dataset. If there's any data scientists in the room, you will recognize it as the hello world of machine learning. Basically, that's a data set of handwritten numbers and letters. And the goal of this data set is to benchmark whether your machine learning model, not LLMs, but whether your machine learning model can correctly classify the handwritten numbers, right? So imagine it as something like this. It has written this 0, this 1, and you have to correctly label the digit that is in there. In this case, what we have done is remove all the letters and keep only zeros or ones, because that's everything that we can encode in the quantum computer. We test the data set, we load it, and now I'm creating a quantum neural network here, which uses something that we call a feature map. Again, this is a data science concept, a machine learning algorithm, but I'm applying it into its quantum version. It's almost like a quantum version of a feature map. I create the circuit for that, and the circuit is simply this. Now, what this is doing is creating random angles in my circuit. It looks like this. When I implode this quantum gates, it's something like this, and that this has these weird numbers. Those are just rotations. So effectively, we're moving randomly the qubit state everywhere in the sphere, almost like the way we initialize a neural network. Now, what we do after we have here is measure the qubits and have a backpropagation algorithm that, instead of training the weights on our classical neural network, it trains the angles on the quantum circuit, so that we can use this superposition to some level of benefit, measure better the neural network. Then we train the model with the usual way, getting the laws, getting all the right epochs and so on. We plot it, and then finally we get the output of the system. So I know it was a lot, but at least you got a glimpse, hopefully, you got a glimpse of quantum computing is complicated, but not that difficult if you already have a good basis of Python and so on. And this is the right moment for people with normal coding skills, engineers, to come into the field and put those engineering skills at work. Me, I am not a PhD in physics. I am an engineer. I've been a classical engineer for many years, and I can say that now is the time for a computer scientist to get into the field and start applying that within the domain. So I'm gonna pause here, and I don't know if there's any questions or everyone fell asleep.
In
Yeah,
case you need help, I'm
Sridhar
good.
here.
Yeah, go for it.
Yeah. So while running this demo, so we were running it in a simulator, you said, right? So this is, so Qiskit is IBM's library. So we are using those Python libraries. So when you are
Yes.
actually running it on a simulator, where are we actually executing it? Is it
So it is, what I showed you was being executed in my laptop. You can simulate
okay?
16 qubits perfectly okay, roughly. Yeah, I
16
mean
is the
more if
limit for that. Okay.
roughly, yeah. You
Yeah.
can maybe get to 17 or so. Think that the more qubits you have, the bigger the matrices grow. So it's almost
Yes.
like the challenge of can you run a 70 billion LLM in your laptop? Because you cannot
Correct.
hold
We
all
don't
that
have.
stuff.
Yeah.
Th-
Yeah.
This is the same thing. The matrices grow exponentially. So 16 qubits is fine. Uh,
Okay.
and that, and but this same code, you can run it on IBM's quantum computers, the 5 qubit
Right.
devices, and you can say, hey, I'm running something on a quantum device. It's a really good exercise because then what you will get is a ton of noise on
Okay.
from the chip.
Okay. Which is not there in the simulator, obviously, because it's just a similar software simulation. So
That's exactly right. You could
yeah.
also
Okay.
use AWS has a service called Bracket that allows you to connect to Rigetti computers, IonQ computers, and a few others. Azure
Okay.
Quantum does the same thing. So within the same infrastructure, and it's really easy and free to start playing with this.
Yes. Yes. All right. Thank you. Thank you very much.
My pleasure.
Anyone else?
I can show you quickly one website. Now,
Yeah,
I
go
will
for
put
it.
it here in the chat because it's probably one of the best sources for learning this stuff that I've used. I used during my stay in this. This comes from one of the quantum experts in the world. This is his website. It's called Quick. It's a few years old already, and it's a JavaScript library where you can drag and drop stuff. So you can open some templates like the Grover search. This is the same one that I showed you before. These are the NOT gates, the Hadamard gates. This little thing is what shows you the probabilities for each state for 5 qubits, right? So 2 to the 5. And those, and the oracle and the diffuser. So in this case, if he built the oracle so that the solution is 11011, right? This one here. The oracle looks like, I don't know if you can see it properly, looks like this. But you can go and build your own circuit. So you can say, all right, I want to put a Hadamard here. I want to put a control gate here. And this is one very important state. We call it the Bell state. And this is what makes the difference from the spinning coins. We have 2 qubits or 2 coins spinning. We put in superposition only one of them. And now when we measure all of them at the end of the circuit, that we can only have either 0, 0 or 1, 1. That's it. There is no chance in this circuit that we get 0, 1, and 1, 0. Now, if you throw coins, you know that is not possible. If you throw 2 coins, you can have the 4 possibilities with roughly equal chances. But in this circuit, 50% chances, 0, 0, 50% chances, 1, 1. And this is a really important state. Anyway, you can come here and you can start adding quantum gates. You see, now I
And then we
changed
can keep on adding gates and then eventually only have one of the state, right? Here.
exactly. You can add as much stuff as you want. And this is pure JavaScript. So it's Yeah. So I really recommend you guys coming in and playing with this. All right, that was a mouthful.
Thank you very much. So if there are no more questions, I would like to thank you for this presentation. This was amazing. This was a whirlwind, but it was an amazing whirlwind. Thank you. Really appreciate
Happy to be here.
This is
Yeah,
amazing.
really. Thanks. The lack of questions is not for lack of interest. It's just, it's really deep thinking. I don't even think the questions I have would be relevant to what's real.
That's all right. That's all right.
Superposition
Really
the
cool.
questions.
It's fascinating, though. It really is.
You know, Matt,
Well,
can
at
you
least you-
superposition the questions?
What's
You
that?
can always do that.
Can you superposition the questions?
Superpositions of questions. Yeah, I think I just did. All the possibilities are in me.
Anyway, I'm sure in the internet we will keep talking about quantum from different angles, but the goal today was to demystify it and say, look, this is just Python code and some simulators. And we went very far over everything.